How's it going, everybody? My name's Dave Roberson, and I'm going to show you how I made this aluminum chicken from my chicken coop using my 3D printer and the ages-old manufacturing method of sand casting. Sandcasting has fascinated me for a number of years. I've been doing it on and off for quite a while now. It's a very important metal fabrication process. It's perhaps the oldest form of mass production, dating back to China in 650 BC. The one fact that really gets me is that if you're in a building, you're probably no more than 10 feet from an object that was created from sandcasting. Our student chapter of the American Foundry Society, on a fairly regular basis, puts on casting sessions. These sessions are open to students and pretty much everybody at UTEP. We have a pretty good turnout, and it's kind of become ingrained in our culture as a department. And as a professor, it's always very awesome and very cool to see students get involved and have fun with something that's a small facet of their chosen major. These sessions have also become good ways to welcome people to UTEP and also say goodbye to people when they leave UTEP. Typically, when we have graduating senior officers, we have them perform the final pour of the semester. Recent world events have put a temporary halt to our casting sessions, so I opted to take up backyard casting. There are several individuals on YouTube who have set up their own backyard foundries. One individual is the King of Random, who shows everybody how to make their own simple furnace out of household items like a bucket and plaster. Other individuals on YouTube have taken this design and modified it. They've swapped out plaster for refractory cement. Other people have also done propane burners as well. This initial design ran on charcoal and some sort of fan to blow air into the furnace to up the temperature a little bit. There are several good examples of material selection for foundry making on YouTube if you look hard enough, so it's really, really cool. I totally enjoy watching people take up this art. We had a student named Luis who graduated in the spring of 2020 who set up his own backyard foundry as well. He shared his journey on Instagram. He started off burning charcoal, and then he upgraded his furnace to run on propane. And it was really, really cool to watch. And it served as some inspiration for me taking up my own backyard casting adventure. So I just wanted to acknowledge Luis. I opted not to build my own foundry or furnace. I ended up buying this small furnace from castingfurnace.com. When I get supplies, I either get them from Amazon or this other vendor named PMC Supplies. I'm not paid by these guys to say this. I'm just letting everyone know where I get my supplies in case you want to set up your own backyard foundry.
Here's the furnace straight out of the box. As you can see, it's kind of small. The furnace comes lined with wool, with basically a ceramic wool liner, and it's pretty soft. There's some problems with the ceramic wool liner, with the ceramic particles aerating, so the furnace comes with this bag of mortar. I didn't like the idea of coating the furnace with mortar because you're putting something hard on something soft, and that can cause some problems because the mortar will just kind of break off. So what I did first was I got this stuff called Simwool Rigidizer, and it's basically colloidal silica. And I put it in a squirt bottle and just sprayed the inside liner of my furnace. And we'll take a look at how that came out.
After about 2 days curing in my garage at about 100 degrees, actually, the rigidizer had rigidized the ceramic wool. You can tell by touching it, it's a lot harder than it was, and that's pretty much what I wanted. I didn't want a soft surface to put the mortar on. I went ahead and coated the furnace with the mortar that came with the unit simply because I had it. I could have run the furnace a little bit more safely after it was rigidized. The whole idea of coating your ceramic wool is so you don't aerate the fine particles and have that become a breathing hazard. And so I took the mortar that came with the unit and combined it with DI water. There was no ratio instructions. It said to mix the mortar until you had the consistency of ranch dressing, and to me, this was the consistency of ranch dressing. It was easy to apply to the inside of the furnace with a paintbrush, and so I took a cheapy Dollar Tree paintbrush and just painted it as if I were painting a wall. And if you've ever painted a rough surface like a wall or cinder block, you know you have to kind of get the mortar into the nooks and crannies, so it took a little while. I'll spare you the details. It took me about 30 to 40 minutes to get it done. And I ended up with something like this. This is exactly what I ended up with, a muddy looking furnace, which is what I wanted. The coating was pretty well. Since I rigidized the ceramic wool, I had more confidence that the mortar wasn't going to flake off upon use, and it was a little bit more resistant to impacts, like if I hit the crucible on the side of the furnace or something like that. One thing that this furnace has that I really like is it has a really good burner, and you can adjust the intake by moving the cylinder over these small holes. So you have 3 holes, so you can adjust the amount of air going in. This furnace also has a stainless steel tip, and the manufacturer recommends that you coat this tip with mortar. However, the thickness of the mortar isn't supposed to be that of ranch dressing, but more like that of paint. I didn't make a video of that, but I made a thinner slurry-like mixture of the mortar and dipped the burner into that, and then assembled the furnace. I then subjected the furnace to a test run, and it was pretty cool. You had a nice blue flame, and it sounded like a jet engine, and that's pretty much what you want. I let the furnace run for about 5 minutes with the lid closed, and then I turned it off, and this was to make sure all of the moisture was baked out of the furnace, so I wouldn't have any problems with gas trying to evolve from the furnace.
All right, so we have our furnace set up. We have the propane, we have our little furnace, and then we have our clay graphite crucible. And before you actually expose the crucibles to metal, I usually treat them with borax. Some crucibles come with instructions telling you to use boric acid. I've always used just plain old commercial 20 mule team borax, and we'll kind of go through that right now. I've not really come up with an exact science for how much borax to put in the crucible. This is a number 3 clay graphite crucible. I usually fill it up to about maybe 1/4 of the way to the top, and then melt it in the furnace. Once the borax is liquid, you kind of use the tongs and swish it around a little bit to coat the inside of the crucible, and then pour the excess out.
All right, so we've melted our borax, and I'm cutting off the furnace by turning off the gas source. So when you turn off a furnace, you always want to turn it off at the source of the fuel, so the fuel that's trapped in the line burns off. It's very hot, so I'm using tongs to open the furnace. I'm using small tongs to open the furnace and also to take the crucible out. I use different tongs to pour. I don't believe in pouring by holding the rim of a crucible. I see other people do that, but in my youth I actually broke a full crucible, and it's kind of, that memory is stuck with me ever since. So I use larger tongs to pour and to handle the crucible like I'm doing now. Inside you can see the molten borax. How hot is it? Well, the melting point of borax, also known as sodium borate, is 1369 degrees Fahrenheit, 743 degrees centigrade. Now is a good time to talk about PPE. So I'm wearing a face shield, a flame-resistant shirt, thermal gloves, and steel-toed boots, and also a leather apron. I'm embarrassed looking at this because I have a hole in my pants. And from my point of view, looking up, looking down, or up, looking down, it looked like it was more well covered than it looks in this video. So don't ever wear holey clothes. I made a mistake, and I need to point that out now. It looks like I'm trying to give a cat a bath, but I am swirling the borax around in the crucible to try to give it a good coat. Borax has many uses. Laundry booster is what it's sold as. You can use it as a cross-linker when you're making slime out of glue with your children, which I often do. And it also works as a good fluxer, which is the application here. So by coating it, I'm effectively making my crucible self-fluxing.
A great example of how additive manufacturing has disrupted sandcasting in a positive way is the development of machines like this one made by X1, which is a binder jetting technology. And binder jetting is really interesting because you can print metals, polymers, and ceramics. In this case, they're printing sand, and they're printing the sand mold. Later on in this video, I'll show you the process of how I manually hand-packed an oil-bonded sand. But there is technology that you can actually 3D print the sand mold. Here's an example of a mold that America makes in Youngstown, Ohio, where they've printed the mold and the core so you can cast something that's hollow. These printers are interesting, but they're quite expensive. I don't have that in my garage. So I downloaded this chicken from Thingiverse, and I slightly manipulated it using this built-in Windows software called 3D Builder. I added these two holes for mounting it with screws, and went ahead and printed it on my 3D printer that I have in my garage. And so a very quick process. This is just a simple fused filament fabrication or FDM based 3D printer. Use this to make the mold. I was actually going to just put the 3D printed object on the coupe and decided to make a metal version. There are some flaws with this that I'll address later in the video, where this mold wasn't designed for sandcasting. It really wasn't even designed to be a mold, but I decided to use it as a mold anyway. And we'll cover some differences between this and something that we actually designed for sandcasting in a little bit.
Here's an example of how we use additive manufacturing to help our sandcasting process. So we're not printing sand per se, but we're using 3D printing to make the tool that imprints into the sand. And what I mean by that is this whole assembly here. So this assembly is called a match plate. And we make the match plate by 3D printing small objects and then gluing them together on this piece of wood to make the larger assembly. There are some features to a match plate, and some people use terminologies like gate and runner interchangeably. But these little blocks here are called risers. I would call this little line here between the two risers the gate, and the runner is kind of in situ because it becomes the handle for the pick. We facilitate packing sand around this by using a flask. And a flask is composed of two parts, the top part being the cope, the bottom part being the drag. Not entirely sure the etymology of these words, but that's what we call it. In between the cope and the drag, we have the match plate. We pack either side, typically the drag first, and then the cope. We would then insert this sprue in the top, line it up with the riser, and we typically have another little tool like this to act as a other riser. So one side's the sprue, the other side's the riser. You pour the metal into the sprue. Hopefully it comes out the other end on the riser so you know you've filled your mold. 3D printer companies typically just print the sand. Okay, so the sand printer example I showed you before prints the sand that's being manually packed. Interestingly enough, we've received molds in the past from X1. Extremely grateful to have that. They do away with the etymology of cope and drag, and they just called their molds top and bottom.
If we take a look at the output from the match plate I showed earlier, you can see that the part has some taper to it. That taper is purposely designed into the mold, and it's called draft. And what draft does is it allows the sand to release from the mold when we separate the match plate from the cope and the drag. On the other hand, if we take a look at this chicken that we're going to use as a mold, you can see that there's absolutely no draft at all. And so there's potential for the sand to actually stick to this part when we remove it from the sand itself. And I'm not using a match plate this time. I'm just going to kind of pack the sand around this. There's also these mounting holes, which could be problematic, and kind of these small features that may not fill all the way with metal. All right, we're about ready to cast. We have our small crucible that we coated. We have this flask with the cope and the drag that I made out of scrap wood. We have Petrobond, which will hold the shape and act as a temporary mold. We have the 3D printed chicken that we're going to use to make an imprint. We have plenty of propane. Our raw material of choice today is recycled cans. Okay, this is a tip that I found on YouTube. It's good to have a pool to melt your cans in, so I have some scrap aluminum that I'm going to get going with at the beginning. I also have some talcum powder and a brush to spread it to keep the top and the bottom of the mold from sticking together, and some small implements that we'll use to help make the mold. The other camera ran out of battery, so we're about halfway done with the packing process here. I'm going to take out the two little tubes I use to make basically the plumbing for the metal to flow through, and I'll remove the plastic chicken part. Alright, we added some plumbing so the metal has a way to flow to the chicken, and then we'll put the top part of the mold back on and get going. All right, kind of a great reveal. I probably should have filmed myself opening the mold. Would have been a little more dramatic, but I'm not using a tripod right now. But at first glance, it looks pretty good. You can see here how I kind of overdid it when I dug the gate by hand. But that can be cleaned up with a Dremel. I was going to have to cut off the gates and runners anyway. And but first glance looks pretty good. I even got the little detail from the chicken legs there that matched the original mold. Didn't quite get the holes. You can see, I don't know if you can see, but you can see, hopefully you can see that the sand kind of got stuck in the holes. And again, this wasn't designed to be a mold in the first place. And so that was kind of expected, but I actually have a good spot for where the holes need to go, so I can just drill it with a drill later. A little bit of post-processing, but not too bad. I'm going to take it out of the sand and we'll take another look. All right, everybody, I've broken our cast chicken out of the sand. I'll go over just a couple little things and then I'll clean it up and show you how it turned out. This is the side I poured the metal in, so this is the sprue. This is the side that the metal came up, and actually let me know I had filled the mold. That's the riser, and in the video of the pour, I indicated that filled metal in the riser was a good thing, and it actually is. You can see the fill's pretty good. I had very little. I don't even think I had any flash, which is where a metal seeps in between the cope and the drag of the mold, so I don't see that. I pointed this out before. I had hand dug the kind of the plumbing, the runner, and so I made a little bit of a mistake there. That was hand done. I've said it before. If I'm doing something mass production, I typically make a match plate that has the gates and runners already pre-made, so I'm going to have some better manufacturing practice. But this was just the one-off. I might have a little bit of difficulty cutting this off. I'm going to use a saw and a Dremel to kind of clean it up, and I'll show you how it turns out. Alright, I'm still kind of in the cleaning process. I just ran it under the garden hose a little bit, and some minor flaws here from where I kind of broke the sand pulling the printed part out. You can see the raster lines. I always like that, actually. Some people may think of it as a defect. It's actually an artifact of the 3D printing process. I tend to leave that on the castings I make from 3D printed molds, just to kind of pay homage to 3D printing, and also I kind of like the way it looks. And I kind of had mentioned I mess up the screw holes a little bit because they didn't have any draft on them, but there actually is enough to serve as guides to drill, so it shouldn't be too difficult to drill the screw holes to mount this to the coop. And overall, it came out pretty good. That's the top of my my sprue. Sorry about that. The back side of the chicken, pretty nice as well. So when I get it all cleaned up, I'll show you guys how it looks. All right, I used a coping saw, and actually probably the wrong blade for this kind of thing, but I used this here coping saw to cut off the sprue in the riser, and we can kind of compare our original printed chicken with the one we cast. And again, this wasn't designed to be a mold, so you would expect to see some defects. The biggest defect I see is I lost some detail here in the chicken foot, and it's probably because this may have been too small for the metal to fill, so it froze before it got to that kind of fine part. And kind of the same when you kind of compare the tail feathers and the little kind of crown here on the chicken. But overall, not bad. I maintained the detail, so you can see there's 2 feet, and you can see that the little beak here is at a different plane than the rest of the chicken body. So overall, not a bad job, and hopefully you guys enjoyed the process.